All right. I basically want to capitalize on what Tim said, and I didn't have a dog, but these are two papers that I wrote years ago. And by the way, the College Math Journal is all freely available. All the back issues are available. If you're a member of the MAA, makes it worthwhile doing it. This particular talk comes from the International Journal of Math, Education, and Science and Technology, which is a British journal, but which is offered freely by the MAA. So you can go to your MAA membership site and you can search for Tim Pennings and you'll see the articles that he's written in the College Math Journal, or you can go to this journal and see the ones I had. I wrote for this journal because I was the editor of Primus at the time, and I really didn't want the conflict of interest of publishing my articles in the journal that I was editing. So anyway, so here's the question. If you permit, I'm having trouble going one screen. If you permit cars to drive as the crow flies, in other words, you don't have to go by streets, you can just go linearly any direction you want, and you have a 1 point neighborhood, a mall that's 1 point thick, what would a 1 hour neighborhood look like that? In other words, what would the region look like so for those points you could get to within an hour? Any ideas of what that neighborhood would look like? No? Okay, I think you do. So if you permit cars to drive, say 30 miles an hour, the neighborhood would look like, in this case, it doesn't look good. This is like 20 miles an hour, right? All those spots that are within 20 miles, people could get to if they could travel 20 miles an hour, okay? So the question is, in this problem, what if you introduced a high-speed highway? Okay, this is like two different ways of traveling. Low speed throughout the community at 30 miles an hour, and high speed along a highway. This is like Elvis's issue, you can swim, you can run. And so the question is, if you're at some point in this neighborhood, how would you get to the mall? Faster than maybe otherwise. And more importantly, could people who are not in that neighborhood, because of the fast, high-speed highway, get to the mall at all within an hour? And so here you have the Elvis problem. If you are on the highway, this is Elvis running, and then Elvis swimming. So if you're on the highway, what you do is you try to find out, is there can I get to the mall faster than just going directly at 30 miles an hour by taking a high-speed highway, cutting off, and heading towards the target. And of course, we're not assuming off-ramps and spirals, and we're doing very, very simple points. So the question here is back to Elvis. If he starts here, where should he cut? And that's the problem that Tim has shared with us. And so if you started, somehow my screen is responding slower than, so if you try to find out that distance, that's about 10 miles north, no matter where you are along that highway, as Tim pointed out, you're going to cut in. Even when you go far, far out, you're still going to use that same cutting point. So now what you do is you say, well, what if you were within the highway? And I think I have one of those, but I can't get my thing to scroll back. But if you were within that circle, it takes a little while. And I've done this in class many, many times. So students will argue and they'll go to the board and they'll draw pictures. What is it, if you live where my hand is, up in the northeast corner, do you just take the regular road over to this point and drop down? Or do you drop to the highway and go on the highway and come down? Not quite the bifurcation, because I didn't do that kind of analysis. And then here's where it starts to get interesting. If you're outside the circle, is it possible that by dropping onto the highway, you could get to the mall within an hour? And what are the collection of new points outside the circular region that could be included in a 1 hour neighborhood of the mall. And so sometimes I just ask students to draw what they think it might look like, this outer neighborhood. In other words, how many more of these people out here can get to the mall within an hour by virtue of taking advantage of the thing. And one of the things students do rather quickly is they say, well, let's see how far out he can go if he was on the highway. So if he lived on the highway, he could zoom along and then cut in. What's the furthest point? So they do that kind of analysis. And then they realize that means you can't live further out and further along. You know, you have to live sort of like somewhere in the middle here. And one of the things they do is they form a function for, I'm jumping through, how did you do this, Tim, when you got success by going one at a time and I'm going ahead? Yeah, that they, yikes. Okay, so they get
arrows on my keypad.
yeah, that's what I'm doing, but my keypad is not working as nicely as it should. But the point is they get a function for the time it takes in terms of those positions A and D. I apologize. And what they find is that there's a linear boundary out here, and they construct that boundary. And they also find out that people south of the highway will actually go up to the highway. And there's an interesting issue about where do they cut in here? Is it the same angle as they cut off here? So there's all kinds of notions that come up in this problem. And I really want to just leave you there. And you can always go to the article and find it. And the article is called Getting Mauled. Okay. So this is an article, same principle of path of least time, but it's used in terms of light. And it's essentially saying, and you know this because you, when you're in a swimming pool, you look through the water at a ball that's on the bottom of the floor. And it's not where, when you reach for it, it's not where you think it is. And so the question is, this is the view you would have of a ball without water. Your eye would be here and you could see to a point of tangency, but you could not see beyond that. Okay, and you could see to another point of tangency. I'm using a circle. I'm changing this from a ball to a circle, but it's the same analogy. One of the questions you might ask is, if you move further and further away, could you see more of the ball? And I think most of us know if we move to the point at infinity, we could see exactly half of the ball because these tangents would be both parallel to each other. So the questions are, in this situation, what can you see? And you have the students compute that. And if I can get to the next one, this is a chart that says, if you move further and further out, you can actually see more of the circumference up to a limit. You can't see around the diameter. But if I can get back, yeah, I can get back, yeah. So if we look at this, this is an eye looking at the circle underwater, but what happens is the light refracts, it bends. And this is another exercise in and of itself by saying, if we assume Fermat's principle, which says the light travels in the least time, what path does the light actually take? And what you get is, if this is the angle that the light would go to the water, and this is the angle that the light would take in the water, there's a relationship between the two angles. And that relationship is a calculus problem, minimizing the time. And I'm trying to get to the next slide, and it's still balking at me. And that's Snell's law that says the sign depends on the velocity, and the velocity of light in water is different than that in air. And so you can play with this kind of relationship. And what we get is the actual path of the eye is to move along in this direction, and then the light will bend. But what you perceive in your brain is that you think the object is along this line, but it really is nearer to you. And that's the perception that you have when you're reaching down at an object at the bottom of the pool. So one of the things that I just want to point out in this article is that you can quickly then ascertain that you can actually see more of the object because of this picture, if I can get it, then you could see to this point to the right, whereas before you could only see to this point. So you can see more of the ball when it's underwater than when it's above the water. And this is the difference. So if you're at a height h above the surface of the ball of the water, when you're at about 5 meters, the difference is significant. When you're at 20 meters, the difference is not that significant. So you can get to this curve. What I think I want to do is stop with this sharing because I'm not very good at it. But the point is, those are 2 articles that use the same principle that our dog friend is using. And I just wanted to point out to you that you can get amazing answers from students. And what I have found is that I taught this at the Air Force Academy, and I had a similar problem. You can fly your jet over enemy territory, but you have to fly at this speed because you want to fly low. And at a non-enemy territory, you could fly higher, so you get less friction, so you get better speed. What's the path you should take to deliver some goods, or just to get from A to B if you have to go through enemy territory? So all the students started working. I had these 2 kids in front of me. They didn't do anything. They didn't write anything. They didn't say anything. They just sat there with a smirk on their face. So I, at the end, I said, all right, everybody take to the boards and put up your solutions. And they didn't even go to the boards. And I said to them, okay, you got to talk to me about what's going on there. And he said, it's absolutely simple. You never fly over enemy territory if you don't have to. So clearly you just go L-shaped. You don't do this cutting across because life is more important. And I went like, what a lesson, you know. I had an Army officer in a classroom at West Point that he converted the terrain of his classroom into swampy terrain. He had fishnet all over the place, and he had a company designed to work as a team to decide where they were going to attack this unit and over what terrains they should go in order to minimize the time for that. So you can get lots and lots of mileage. That's not meant to be a pun, but you can get lots and lots of mileage from minimum time over distance. And I'm glad to complement what Tim is doing with 2 other examples. And you probably have lots yourself. And if you do, by all means, write them up, submit them for journals, submit them for publications at online sites, and maybe you'll get a letter from the Queen's right-hand man as well.